Welcome to this explainer. We're jumping right into the internal software logic powering the SPAM150C motor protection relay. Look, if you're working with heavy-duty AC motors, especially out in brutal offshore environments, you already know this IP54-rated aluminum box is your primary line of defense against catastrophic winding failures. But here's the thing. The real magic? It's not just in the hardware, it's in the configuration.
It's a fascinating paradox, really. You can take two physically identical SPM150C relays, mount them right next to each other on a panel, and they can behave completely differently on the exact same motor. How does that happen? Well, it all comes down to their switchgroup configuration. This is where the actual customization happens. It's this hidden layer of logic that transforms a generic, off-the-shelf relay into a highly tailored protection scheme, perfectly dialed in for your vessel's unique operational profile.
To really wrap our heads around this, we need to break this configuration down into three specific layers. First up is SGF, which stands for Switchgroup Functions. Now, the easiest way to think about SGF is to picture it as your rule changer. It's the logic layer that dictates your optional protection behaviors and actually alters the relay's fundamental rules during really specific high-stress conditions, like a massive, heavy motor startup.
So, in practice, what does this look like? Well, SGF lets you automatically double the high-set overcurrent threshold right when the motor starts. It basically bends the rules temporarily, so a totally legitimate starting surge doesn't trigger a false trip. And it gets better. It can actually inhibit the earth fault protection completely if the phase current spikes above 4, 6, or even 8 times the nominal current. By doing that, the relay basically says, hey, this massive surge is normal. Let's not accidentally trick the low-set earth fault detector and shut everything down.
Okay, so that brings us to our second layer, SGB, or switchgroup blockings. If SGF is your rule changer, then SGB is absolutely your traffic cop. This entire layer is dedicated to handling traffic, routing incoming blocking signals, and managing exactly how external trip commands get integrated and latched directly into the relay's memory.
And how exactly does this traffic handling play out? Well, SGB gives you the ability to take an external digital input, usually labeled as BS, and route it to act as a speed switch. This is an absolute lifesaver for stall protection on drives where the safe stall times are strictly limited. It also lets you configure a trip output to actually latch. So once it trips, that output stays locked in, glowing bright red, until an engineer physically walks over and manually resets it. And finally, SGB is the layer that lets you route external trip orders from entirely different ship systems straight into this specific relay.
Now we hit the third and final layer, SGR1 and SGR2, otherwise known as the switchgroup output relays. This right here is the physical handover layer. Up to this point, the relay has been doing all this complex internal number crunching using SGF and SGB. But now it actually has to tell the outside world what to do. SGR standardizes exactly which physical output wire an internal alarm or trip command is going to travel down to hit your breakers or alarm panels. This is crucial because SGR is effectively a routing matrix. It links specific internal faults directly to specific signaling outputs. For instance, you might want a thermal prior alarm to route to signaling outputs SS1, SS2, or SS3, just to give the crew an early warning. But if it's a critical stall trip, a high-set overcurrent, or an earth fault, SGR routes that straight to the main trip output, TS2. It's the ultimate switchboard, completely defined by the software settings you punch in.
All right, let's put this all into perspective with a quick real-world check from our source material. Imagine you're commissioning a vessel, right? You've got this massive motor, and its starting current regularly hits 5 times nominal. But here's the headache. You are getting nuisance earth fault trips every single time you fire up the motor, and it's completely halting operations. Based on the 3 layers we just walked through, which switch group is the exact tool you need to fix this? I'll give you a second to think about it.
Got it? Yep. The answer is SSGF, the switchgroup functions layer. Because you know that starting surge is always going to be 5 times nominal, you can just hop into SSGF and configure it to inhibit the earth fault protection anytime the current crosses that 4 or 6 times nominal threshold. The relay temporarily ignores that perfectly legitimate surge, your motor starts up as smooth as silk, and those annoying false earth fault trips, completely eliminated.
So look at what we've built here. You now have a complete functional configuration map of the SPAM150C.
You've got SGF for dialing in those optional functions and bending the rules during starts. You've got SGB acting as the traffic cop for blockings, speed switches, and external trip routing. And then SGR1 and SGR2 for that final output relay assignment. This right here is exactly how standard, identical hardware transforms into a highly tailored, vessel-specific protection scheme.
And that brings us to the ultimate handover. Step 1, the relay logic securely and accurately decides exactly when it needs to trip. But step 2 is the actual physical action. The relay has to hand that command over to the switching hardware, which out here is often a V-contact vacuum contactor. And that leaves us with a pretty provocative final thought to ponder. What happens when this incredibly smart, lightning-fast relay hands a critical fault command over to a vacuum contactor that inherently has a limited short-circuit breaking capacity? I mean, how does the physical hardware survive the sheer violence of the fault the software just detected? Keep that in the back of your mind as you explore the mechanical side of power protection.